So this is 1 minute past 7, so we should get started. 我们准备开始了哈。那欢迎大家来参加这次的竞赛。好，那因为我们有外籍生哈，所以我们再来就用英文。OK， 好。Our foreign students, so we'll use English for this forum, and I guess this video conference is recording, so you can view this later in our CA channel. A few things before we get started. 好，那有些事我先宣布一下哈，尤其是几位硕一的学生啊，我们这规矩我们这个竞赛的规矩你可能要理解一下。好，还有一些博士班学生哈。Hello， 有谁没 mute 请 mute。那这是谁？宇翔哈 ，mute 掉。OK， 好，那个同学要 mute 哈，在你还没有发言的时候，请 mute。好 ，please mute。All right， and raise your hand if you want to speak up。我先把一些这个前言稍微讲一下了哈，所以几位目前的硕士班学生跟博士班学生大概理解一下我们怎么推行这个竞赛。好，那基本上我们从大概3年前吧，我们就开始有这个所谓的院长奖的硕士论文竞赛。那我们组非常公平哈，我们组就是各个老师会推荐一位同学上来，那就像今天这样，每位老师推荐一位，那会上来做一个比较，那所有的评分呢就由老师们决定，最后推荐一位来得到这个院长奖。那这是一个荣誉，那也很不容易了哈。好，那从今年开始我们有2个名额，那也不是从今年开始了，就是说我们今年有2个名额，所以今年会有2个院长奖。但是今年比较特别的是，其中有排序第1的院长奖呢，我们会推荐到系上，进行校长奖的比较，所以这个我们今年多设了一个校长，这个校长论文奖，这个就有因为我们的院长去当校长了嘛，所以就把这个奖也带过去，OK， 所以就是 even greater honor So for those students who is currently a master or PhD student, you are all eligible for the competition. And our competition basically is open, and every professor's group can have one candidate for the competition. And today we have 4 candidates. Okay, and the good thing is you have 50% to get awards, because we have 2 persons that can be recommended for this Dean Award, and the one on the first place will be recommended for the President Award. OK， 所以我们今天这个非常竞争，但是好事是有50% 你会得到这个奖哈。我们有4位同学，我们会有 you have 50% chance to receive the award. 那as this is a competition, the rule had to be fair. So what we're going to do is we're going to give you 12 minutes to speak up all your achievement and impress us, because 5 professors will rank based on your performance today. Okay, every candidate has 12 minutes, no more, no less. Well, you can, no more. Okay, I should say no more. All right, and as I'm a chairman, I'm going to mute you if you exceed the time. 好，那这个我讲清楚哈。我们基本上在这边哈，因为我要提醒你说几分钟到了太麻烦了，12分钟我就自动把你静音了，所以你不用再讲了。好，不管你讲到哪里，所以请自己看着自己的表。好，那我们有一个计算的时间了哈，我会建议就是你开始 present 的时候你就开始按码表，然后你跟我讲你 ready 了，我说 OK， 我就按我的码表，所有的表一定是比你慢。所以如果你的表都超过12分钟你还不停，而我的表超过12分钟我就把你 mute 掉了哈，就没有了哈。那你这个我们今天的 performance 是看你今天的表现哈，所以如果你连这个都控制不好，我想会影响你的这个评分哈。 Okay, so let me say this clearly. So you have 12 minutes, and I suggest you indicate a signal. Let me know you are ready, and I will press the stopwatch here. Okay, and when it exceeds 12 minutes, I will mute you, and basically we move to the QA session. Okay, and in general, we have 3 minutes for the QA, but as professor might be more curious about your work, so you could take more time, and I think that's okay. I'm not going to count the time on the QA session. Okay. Now, before we get started, any question? 那几位老师不知道有没有什么要补充的哈 ？Okay, if not, we'll start with the first presenter. 应该是罗凯云嘛哈。Our first presenter will be 罗凯云, and when you present, you probably want to open your camera so we can see you. And the second presenter will be Jimmy Jin, and the third presenter will be, let me see. 日本年学生，我看一下。Third presenter, let me double check. Oh yeah, 雨生, okay. Third presenter will be 雨生, and fourth presenter will be let me see.
Aritra.
Sorry, Aritra. Okay. All right, so we move to the first presenter, and Kaiyun, when you are ready, give me a signal, and I say, okay, you can get started.
请问听得到吗？
可以。
好。
那你好的就跟我讲一下。你好，开始计时。
好。我好了。
好，开始计时。
Hello everyone, my name is Luo Kaiyun. The topic of my talk today is toward nearly zero energy building, smart energy management of vehicle to building, B2B strategy, and renewable energy sources. And my advisor is Professor Xie Yijun. Oh, this is me. During my master's, I have participated in many competitions, projects, international conference, and journal papers writing. 它怎么不动了？可以这个暂停一下下。哦，我继续吗？
Sure, 请继续。
好 Here is my outline. The first part is introduction. As you can see from the figures below, the building sector is responsible for a substantial 34% of the global share of final energy demand and alarming 37% of global CO2 emissions. With the world's increasing focus on achieving net zero emission goals, these statistics make it abundantly clear that the building sector is a prime candidate for decarbonization efforts. Many governments worldwide are trying to introduce some policies and strategies to achieve the ambitious target of nearly zero energy buildings. However, as we witness the rapid growth in transportation electrification, a new challenge arises. The increasing adoption of EV. 不好意思，那个技术上的问题，它不会动。
不会动。等我稍微给你暂停一下，你第一个我们允许。怎么了？还好吗？我现在时间停起来，没有问题。你
好紧张。好。
可以吗？我时间停着没关系。
好。
来。
OK。
可以吗？
可以。
OK， 那我继续咯。好，我继续。
Okay. This not only intensifies the already high energy requirements of the building sector, but also places additional strain on our power grids. But here is where the opportunity lies. The proliferation of EVs actually present a promising avenue for implementing innovative solutions to address energy consumption and greenhouse gas emissions. One solution is vehicle to everything technology, which include vehicle to grid and vehicle to building. Unlike the V2G strategy, which requires substantial investment in deploying large-scale grid infrastructure, the V2B strategy offers a more cost-effective alternative. One of the key advantages of the V2B strategy is its ability to enable bidirectional power transfer between EVs and buildings. The V2B strategy takes the advantages of the fact that vehicle parked for the extended period of time. During this idle time, the EV battery acts as a temporary storage device for excess energy generated by renewable energy systems. Furthermore, during peak demand periods in the building or when renewable energy generation is low, the EV battery can serve as a power source, helping to alleviate stand on grid and reduce the building reliance on external electricity supply. Previous studies have not yet provided the detailed models required to optimize scheduling process, especially tailored for V2B integration in buildings. Furthermore, it is important to consider the battery degradation costs resulting from implementation of V2B strategy and the carbon emissions resulting from energy use, which are usually overlooked in previous studies. This gap in research highlights the need for more comprehensive studies that consider all the intricate factors involved in V2B integration. Okay, so now let's move on to the second part, methods. Here is the methodology framework of my research. Our main focus of this study is on developing smart energy management system algorithms that incorporate the concept of V2B. To achieve this, we employ a scenario-based analysis approach to analyze and evaluate the energy, environmental, and economic aspect of the system. In the following presentation, I'll begin by introducing the simulation of model inputs, followed by the construction of smart energy management system. For solid power generation simulation, we refer a formula proposed by Wood et al. And conducted simulations based on weather data and the parameters of the solar panels. And the simulation of vehicle parking pattern consists of two components. The first component is vehicle fleet composition, where we concentrate on technical economic characteristics of the top 5 best-selling EV models. By considering the proportion of their market share, we determine the composition of the vehicle fleet. The second component is parking time distribution. In this part, we model the parking process of EV using a Poisson process with a determined rate parameter. This allows us to capture the uncertainty and variability associated with vehicle parking durations. In the design of the smart energy management system, there are two objective functions and constraints. The primary objective is to minimize the building electricity demand on grid, and the secondary objective is to achieve peak shaving and load shifting. In the EV charging and discharging prioritization component, we consider time urgency factor to determine the priority of each EV for charging and discharging. And these two figures depict the algorithm for the proposed smart energy management system. The algorithm follows the sequence of ESS discharging, EV discharging, EV charging, and ESS charging, and to conduct a scheduling process on an hourly basis. And next, I'll explain the carbon emission intensity model, which will directly affect the result of the environmental analysis. We employ a carbon emission model proposed by Zheng et al. To comprehensively quantify the changes in carbon emissions resulting from the implementation of SENSE. And next, I will move on to the economic analysis section. In the economic analysis section, we calculate the capital and operating expenditure of solar PV panels and energy storage systems. The building electricity bill is calculated based on the electricity rate schedule provided by Taiwan Power Company. And for battery degradation costs, since extra charging and discharging cycles associated with V2B can cause potential issues related to battery capacity fade. Therefore, we derive a formula that calculates the battery degradation cost posed by each discharge of an EV. Furthermore, we evaluate the carbon emissions from the buildings in an energy consumption sourced from the grid and quantify in monetary terms by applying a carbon price of 10 USD per ton. So after establishing the aforementioned models, this study will proceed with a case study. The target building selected for investigation is civil engineering building at National Taiwan University. Four distinct scenarios has been designed to explore the effect of various elements. And next, I'll introduce our result. The figures on the left is the hourly simulation result of half violin plots with an overlap box plot. On the right is the annual cumulative result of energy and environmental analysis. Overall, the SENS has demonstrated its effectiveness in enhancing energy efficiency and advancing environmental sustainability. The PV plus V2B plus ESS scenario yields a remarkable decrease of up to 65% in power demand on grid and 64% in carbon emissions. And compared to the reference scenario, the extended tail of the overlay box plot and the other scenarios indicate a significant shift toward lower energy demand and reduced carbon emissions. And here is the snapshot of daily profiles and monthly average comparisons. You can see that in reference scenario, the highest power demand usually occurred around 2 to 3 p.m., accompanied by a corresponding peak in carbon emissions. With the integration of PV systems, V2B strategy, and energy storage systems, it may achieve net zero energy buildings throughout the day under certain circumstances. In addition, it is worth noting that the summer months present greater potential for peak shaving. This is attributed to higher solar power generation during this season, which creates favorable opportunity for reducing peak electricity demand. And here is the breakdown of equivalent annual cost results. As you can see from the table, comparing to the reference scenario, the social cost of PV plus V2B scenario reduced 201,000 NT dollar, while PV plus V2B plus ESS scenario increased 3,155,000 NT dollar. This highlights the multiple benefits of PV plus V2B scenario from both economic and environmental perspectives. Lastly, we have the result of sensitivity analysis, where we verify 5 parameters to obtain corresponding equivalent annual cost. The parameters include capacity of ESS, the capital expenditure of PV and ESS, the basic date of discharge, and carbon price. From the presented table, we can conclude that due to the current high capital cost of ESS, PV plus V2B remains the most cost-effective option at the present stage. And conclusion, this study proposed a SENS algorithm that integrates a novel V2B strategy and EV charging and discharging prioritization. And this study also includes an economic appraisal and an environmental impact assessment. Although PV plus V2B plus ESS scenario having the greatest potential for EV saving, the economic analysis result revealed that PV plus V2B scenario is the most favorable option in terms of cost effectiveness. And here is my reference. Thank you so much.
Thank you. Right on time. Very nice. Okay. Okay, now I'd like to invite all the professors and all the audience with a question for Kai-Yun. Any question from the audience? Yes, please.
Yes, I think some of the results are really encouraging. I'm just wondering, because it's a study under certain scenario, I just wonder what's the kind of uncertainty from your results. I mean, because in your base strategy, it's very encouraging that you reach net zero, but what's the confidence behind that?
可以用中文回答吗？
可以。
在结果的部分，首先可以看到，就是在电动车车辆模型这边，稍等我一下，它有点卡。就是在车辆模型这个部分呢，因为我们没有办法得到真实的停放的资讯，那因此我们这边是采用 Poisson process 去进行模拟。那在电动车的充电需求部分，我们也是直接的去假设车辆会在30%到90% 去进行就是 randomly 的就是 assign 这样子。那这个部分是我们就是会去蛮大程度的去影响 B2B 效益的一个部分。对。
OK， 那你最后出来的结果是是平均？你秀那 curve 是平均还是就是最好的情况？
是说那个蓝色绿色那张图。
对。
那个是1年当中模拟结果里面每个小时的 volume plot， 那我是画一半，然后另外一半我画 box plot， 所以它是每个小时的模拟结果。
谢谢。
Any comments or question from audience？ 其他老师不知道还没有什么问题。我问一个问题好了哈。那刚刚你提到说这是一个 multi-objective 的这个 optimization， 那我是没有看到你在哪里做 optimization， 就是你可以稍微描述一下吗？就是你是怎么做这个？是一个 continuous 的 space 的 optimization， 还是一个 discrete 的？那你有你的 maxima minima 代表的，就是你怎么做这个 optimization？ 或是说这是一个 convex 的 function， 其实很简单，还是说就是一个什么样的 function form？
这个部分的话，其实我这边是设了2个 objective， 那我的这个 algorithm 其实是 based on 这2个 objective， 但是我其实最主要的目的是希望可以去降低建筑对于电网的能源需求。然后这2个其实不是 multi-objective 的 optimization， 它其实是属于我在达成降低最大化程度降低建筑对电网能源需求的同时间呢，我们也可以达成就是建筑小风田的目标。所以它其实并不是，我只是提出一个就是 multi-objective 的我的 algorithm 的目标。
你是这是你要算的东西
对，这是我们解决的问题。
了解，就是你要算的东西，所以基本上这是个一个 deterministic 的一个事情嘛，哈，当然你可以有 uncertainty 啦，就是说它没有什么选择，算出来就是这个结果，意思是这样的哈。
因为如果说今天要做 optimization 的话，那我们也许还会再加入成本方面去再进行取舍，但是这同时间我们可能会需要透过一些权重之类的去找到最佳化解，但这并不会是我们就是真正想要达到降低建筑对电网能源需求的那个就是最想要解决的这样的一个问题。所以在这边我们是设计2个 objective， 但主要是希望可以去解决最上面这个问题这样子。
了解 OK， 谢谢。那最后一个我想请教一下，你后面有一个 net zero 非常漂亮哈，但是那个 cost 比较高，我有点搞不大清楚这个你考虑了什么 ESS 是不是？因为很快哈，我没有看得很清楚。第一个什么是 ESS， 可以稍微解释一下吗？
可以。ESS 的话，就是我会在建筑那边再设置一个固定的储能设备，能源储存设备。
了解。
对，因为电池的话，目前就是初期投资成本的金额是蛮高的，所以这也凸显了 B2B 策略在建筑物节省能源以及减少碳排放的重要性。因为B2B 我们可以去利用电动车就已经停放在那里，我们直接可以去利用建筑物周遭现有的资源，在 少量的电池退化成本的情况之下，我们仍然可以达到更大的效益。
了解 ，OK， 很清楚，谢谢。
谢谢。
Any question from the audience？ 老师们还有没有什么问题 ？OK， then thank you, 凯云 for a very nice presentation. We shall let you release your sharing of screen. 那凯云就麻烦把 screen sharing 把它release 掉 ，OK。we now invite the second speaker, Jimmy Jin, to talk about his work. Jimmy, when you're ready, let me know.
Okay. Let me share the screen.
Okay, so Jimmy, you want to, yeah. Okay, yeah, get everything ready. Are you ready?
Yes, can you see the screen properly?
Your sound's a little bit small. You body want close to the microphone. Can you speak louder?
Can you hear me better now?
Yeah, and it's better now. Okay.
Okay.
Are you ready?
Yes, I will start.
Okay, I'm counting the card.
Okay. Good afternoon, everyone. My name is Jimmy Jean. First, a bit about myself. I'm from Haiti, and my advisor is Professor Chen San. Here on the right, those are some publications that we have published over the years, and this work that I will be presenting today is a paper which is currently in preparation. And as for my future, I have received a fully funded PhD position at TUDEF, and this is where I'll be moving next for continuing research. The title of this work is Graph-Enhanced Deep Material Network, Multi-Scale Materials Modeling with Microstructural Generalization. This is the outline of my presentation. First, to begin, the mastery of materials is central to the progress of humanity. Our ability as humans has progressed in the sense of designing more and more complex materials as humanity has evolved. And recently, there has been a progressive shift from traditional materials in several industries to composite materials. However, although the composite materials is getting more and more popular, there are still many challenges that we still need to overcome with that. And an example of that is the disaster that just happened recently with the case of the Titan submarine that exploded just a few weeks ago. And for us to better understand the behavior of composite materials, we need to do that through homogenization methods in the context of multi-scale material modeling. With regard to homogenization, it is a technique that is used to compute the average properties of materials across different scales. And traditionally, there have been methods such as the finite element method or fast Fourier transform method that have been used to do that. However, those methods are usually very computationally expensive. And this has led scientists to instead turn to machine learning-based surrogate models, which are faster to do that same task. And of those surrogate models, there is one model which is very special, which is the deep material network. In contrast to other types of neural networks, which are not based on physics, the deep material network is based on two-phase dynamic theory. We are given a very simple microstructure with two phases and different volume fractions. We can analytically derive its homogenized properties. And this simple solution can be used as the building block for a very more complex network. And this is the basic building block of the deep material network. The deep material network itself has the structure of a binary tree. And at each node of those binary tree, we have those analytical solutions which are stored at those nodes. Now, because the deep material network has physics that is embedded into it, and because the homogenization function itself is something that is independent of material nonlinearity, we only need to train the deep material network on linearistic data. And then when we are actually using it, we can use, for example, Newton's method, and then use the deep material network for predicting nonlinearity. And here on the right, that's just an example of how we can start from microstructure, represented by DMN, and then use that DMN to do nonlinear predictions. However, DMS still has its limitation. Let's say that we have different microstructures, then we need to train different DMS for those microstructures. And there has been some works that have tried to generalize the DMN to different types of microstructures. However, they usually use that process where they start with some descriptors of those microstructures. For example, what is the fiber orientation of fibers in those microstructures, or what is the volume fraction of those fibers. And then they use some interpolation functions of some transformer strategy to then generate different DMNs. However, there's a problem with that because for some microstructures, we cannot even define descriptors for them. And this leads us to our research objective, where we want to develop a graph-based model that can take into account all the details in the microstructures of materials. And then we want that model to generate different DMNs for us. And we also wish that the DMNs that we will be generating for all of those microstructures, they can be used independently of the graph-based portion of our models so that we can use them for very fast online predictions. Now, this leads us to our methodology. In the literature, there are several works that have already established the link between parameters in the deep material network and the geometry of microstructures. And because of that, we postulate that the parameters in our deep material network, which are activations, Z, and rotation angles, we postulate that those parameters, they are functions of the domain of those microstructures. Now, how do we process those domains? We use this framework where we start from microstructures, we transform them into graphs, and we then take those graphs and then we pass them through a section of that we call graph-based feature extraction to receive some feature vectors. Then we take those feature vectors and then we combine them with the parameters of what we call a core DMN and pass them through a section of microstructure informed transformation. And then at the output of that segment, we then obtain new DMNs, and then those new DMNs, they can independently take as input the material properties of different microstructures, and then we can predict the homogenized properties of those microstructures. Now let us take a look at those different segments. For the first one, for the graph representation of microstructures, we start with those microstructures and then we mesh them. And given those meshes, we then take each element in those meshes, we transform them into nodes in a graph. And then for the connection between those elements, we transform them into edges in that graph. And then given this graph, for each node in that graph, we define node features, where in our case, we are modeling composites. And at those node features, we store information such as the area of each element, the coordinate of the centroid of those elements, whether this element is located in the matrix or inclusion of that microstructure, and whether that element is located at the border of a microstructure. Next, for the step of where we extract feature from our graphs, we take our graph and then we pass it to several layers of graph convolutions and fully connected layers. And we also do some pooling so that at the end, we then obtain a collapsed feature vector that is a compressed representation of our input graph. Then given this feature vector, we then turn to the next step where we take that feature vector and then we combine it with the parameters of what we call a deep material network model. And we pass those information to a multi-layer perceptron. And then from that, we obtain outputs, which are none but the parameters of what we call new DMNs. Now we can summarize the mechanics of our model, where we basically start from microstructures at the beginning and then transform the microstructures into graphs, and then we pass those graphs to our GNN DMN model. And combining those graph information with the parameters of the core DMN, we then derive new DMNs. Now let's look at examples of the applications of our model to different types of microstructures. First, we consider microstructures where the inclusions in the matrices of those microstructures are circular and all have the same size. We generate two sets of data. One is a training set with 200 microstructures and a validation set with 50 microstructures. And for all of those microstructures, we sample them so that their volume fraction is between 10 and 40%. For each of those microstructures, we generate different graphs, representations of them. And we also generate material properties, input material properties for our model, as well as the homogenized material properties for those microstructures. Next, we train our model, and then we evaluate the performance of that model on the tangent that it predicts for the microstructures, and also on the volume fraction that it can predict from the deep material network that the model has generated. If we look at the tangent, we notice errors that are around 2%. And if we look at the predicted volume fractions, we obtain errors that are even less than 1%. Now, with regard to the interpretability of a model, the DMS that the model has generated, we can look at its parameters and then from that infer the volume fraction that it has learned from the input graphs. And when we compare the volume fractions from the actual microstructure with the volume fractions that the DMS has computed, and we can see by looking at them a very close relationship between them in the sense that they are very close to each other. Next, we look at the ability of a model to capture the physics of those microstructures. We consider both microstructures that the model has seen during training and microstructure that it has not seen. And we can see that it can learn that as the volume fraction increases, the elastic modulus should increase, and also as the volume fraction increases, the Poisson's ratio should decrease. And if we look, quantify those errors, we can see that they are mostly less than 1%. Next, we use our model for nonlinear prediction, and we see that the predictions of our model, they are very close to the predictions that are obtained via dynamical simulation. Next, we consider more complicated examples where our microstructures are defined by the number of particles in them, the semi aspect ratio of each particle, as well as the total volume fraction of those particles. And we can see the diversity of those microstructures, and we do as in this first example, and look at different types of results, and the performance of the model is very accurate, just like the first example. And to conclude, we have proposed a model that can, in contrast with DMS, handle multiple microstructures. And the model can generate DMS for even microstructures that it has not seen during training. And the performance of our model is very accurate in the sense that we get errors that are around 1 to 2%. For further research directions, we envision that this model can be extended to 3D and to other material systems, and even be used for inverse material design in the future. As to the impact of this work, this approach has got the invitation of the head of the computational and multi-scale mechanics group at NC's LS-DYNA, and it is possible that in the future that this approach will be incorporated into future releases of the NC's LS-DYNA software. And this is all for my presentation, and I would like to hear your comments. Thank you.
Okay, great. Just in time. Okay. Okay. We now invite all the audience for the comment and the question. 我们请老师们或是同学来 comment。
So maybe I can have a few questions.
Please go ahead.
Yep. So very interesting, Jimmy. So I think you start from the mesh of the microstructure, right?
Yes.
So could you talk a little bit more regarding, say, for instance, how you determine the mesh size? And then say, for instance, if later on in the future, what's your opinion regarding this work when it's being applied to composite materials like reinforcement concrete?
Yes, for the mesh size, because for a model, in order to be able to train a model, we need to compute its homogenized properties. So for the mesh size, we've used the mesh size that is suitable to give us accurate results when we compute the homogenized properties. And so we use that same resolution of mesh for constructing the graphs that our model uses when it's converting those graphs into feature vectors. Now the mesh sizes, they are not exactly the same. For example, in this case, we have mesh sizes with elements that vary from about 7,000 elements to maybe 10,000 elements. But they are like kind of close to each other. But if the mesh sizes of the input graph would change, for example, just a few hundreds of elements, then probably the performance of the model might be a little bit different. And that's an aspect that we need future research, I would say, to improve on that aspect in the future. And if we want to apply this model to the behavior of, for example, concrete materials, this is something so far that we have not done in this work, because we've only considered materials that are kind of reinforced with particles. But that is something that I think that future, like people who continue on this work might take into account to see how the model would perform on materials such as concrete, for example.
Okay, thank you.
Yeah, thank you.
Any other question from the audience? 老师们或同学有没有什么问题？
I just have a quick question.
Go ahead.
In some of your slides, you are showing the number like 250 or like 300. How do you get those numbers?
Yes. So we basically started with, because we needed to select a data size that would enable our model to be able to learn that family of microstructure. And when we are designing our problem, we started with 200. And then when we train our model, we realized that it was able to learn from just 200 microstructures. And we also tried to increase it to 400, for example, but we noticed that increasing it to 400 doesn't necessarily improve the performance of our model. So we stayed at utilizing 200 microstructures for the training set. Yes.
Okay. How about the 300 triples?
Oh yes, for the 300, we referred to the original works that have been done on the deep material network. And for them, they've used that number of sampling points for training the network. So we chose that number by just referencing to those works. Yes.
Okay, thank you.
Thank you.
I have a quick question.
Go ahead.
So I noticed that in your page 23, you compare your result with the Leo. So can you like briefly summarize the major differences in the methods or something, why you compare your result with them and what's the major difference? So did your result perform better or what is comparable?
Yes. Because in their approach, they've used some transfer learning strategy to be able to model the behavior of different microstructures with different volume fractions. So our approach is different in the sense that we didn't use a transfer learning strategy, but we use only one model to do those different predictions. So in the end, we looked at the predictions of our model and looked at the trends and then compared it with the results that they have obtained using the transfer learning strategy. And then we noticed that the trends are very similar, which kind of proves that our approach is correct, just like the approach was.
Okay.
Yes.
Thank you.
Okay. Any question from the audience? 其他老师还有问题吗？或是问过的老师也可以再问。If not, we thank you, Jimmy, for this presentation, and then we'll move to the third presentation. Yeah, thank you, Jimmy. You can mute now. Okay, we move to the third presentation by 雨生。
这样有听到我的声音吗？
有。好，
好，
等一下哈。
好，
你准备好了吗
？OK。
Okay, I will start counting the time. 来，开始。
好，大家好，我叫郑宇生，那我的指导教授是汪立本教授。 那我的研究题目是探索三维雷达数据与对流雨包特征演变预测之应用。那这边是我研究的 outline。那首先呢，我来介绍我研究的动机。那近年来，由于全球暖化的影响，极端降雨事件发生的频率也越来越频繁。那目前主要有2种方法可以去帮助我们降低极端降雨事件所造成的灾害。那第一个呢，就是去新建我们相关的基础设施，例如说蓄洪池或是排水设施等。然而这个方法需要花费比较大量的时间以及金钱。而第二个方法就是去建立我们的即时灾害预警系统。那本研究的重点 Rainfall Nowcasting 也是属于这个方法。那 Rainfall Nowcasting 呢，是一个专门用来进行短延时降雨预测的模型。那在现今中，主要有2个模型可以用来进行短延时降雨预测。那第一个是大气模型，这个模型呢，主要是通过解一些比较复杂的流体力学方程或是热力学方程来进行降雨预测的。那也因为这样，它可以预测一段比较长的时间。然而，大气模型在进行预测时，它需要一段的暖机时间来达到它数值的稳定性，因此它在刚开始前几个小时的预测是非常的不准确的。那另外呢，本研究使用的 Nowcasting 模型呢，是通过外插我们雷达的资讯来进行降雨预测的。那也因为这样，它的预测比较短暂的时间。可是呢，因为它是外插雷达资料嘛，所以它在前几个小时的预测是非常的准确的。那也因为这样，它刚好可以跟我们的大气模型进行一个互补的作用。那这个图呢，是我们的雷雨包随着时间的特征演化的示意图。上面这个平面呢，是我们2维雷达的示意图。那我们可以看到，雷雨包随着时间的进行，它的特征，例如像是面积或者是强度等，会发生变大或者是变小的情况。那当我们把它投到3D 的雷达资讯中来看的话，我们可以发现每个雷雨包都有一个雨包的核心，那它会随着时间进行上升或者是下降的情形，而这也是本研究一个很大的启发。那在一般而言，针对对流性的降雨 ，Radar-based Nowcasting 是一个比较好的选择。然而，现今的 Nowcasting 模型它只能够预测雷雨包的移动方向。然而，如前一张图所展示的，雷雨包随着时间除了会发生空间上位置的移动之外，它本身的特征也会随着时间而有所演化，而这是现在的 Nowcasting 模型没有办法去预测的。那另外呢，就是我们可以发现，就是在3维雷达中可以发现一些2维雷达看不到的额外资讯。因此，本研究的目标主要有2个，第一个就是去探索说是否3维雷达可以帮助我们去预测雷雨包本身特征的演化。那第二个就是我们希望可以开发一个 NL 的模型，来帮助我们去预测雷雨包的特征演化。那这是本研究的研究方法，主要分成3个部分。第一个是资料处理以及模型的训练。那资料处理的部分呢，主要是我们运用了一些已经有的演算法来帮助我们从雷达资讯中萃取出我们需要的雷雨包的特征资讯，来让我们的 model 进行训练。那接下来呢，我们会去计算 model 的 uncertainty。那最后呢，我们会针对我们 model 的 performance， 还有我们uncertainty 的 performance 做一个 evaluation。那首先是我们资料准备的部分。那我们首先呢会先利用Enhanced Titan 这个 model 来帮助我们从2维的雷达资讯中去辨识并且追踪出我们雷雨包以及它的移动轨迹。那接下来下面这张图呢，就是我们用 Enhanced Titan 它去找出来的一些雷雨包的本身的特征资讯。那图中这些红色的row 呢，是我们接下来希望能够用我们的 NL model 去预测的一些特征。那当我们利用我们 Enhanced Titan model 把我们雷雨包的时间和空间的关系建立起来之后呢，可以得到如左边这张图所示的样子。那图中这个 XY 代表雷雨包在空间上的位置，然后这个 Z 轴呢，这代表不同的时间点。所以当我们把这个一切的东西观点建立起来之后，这是一个十分复杂的3维的图形。那这边我们参考了一篇2016的 paper， 那该篇 paper 是使用一个 Spatial Temporal Grace Model 来把三维图形降低成二维的图形。那图中的 x、y 一样表示的雷雨包在空间上的位置坐标，而图中这个 C1、C2、C 它则代表不同的 time step。那另外我们也把这个图形作为一个称作 cell cluster。那在一个 cell cluster 中呢，我们的里面的 cell 常常会随着时间而产生分裂，甚至是跟别的雨包发生合并的情形。那这会对我们的研究造成一些困扰，所以呢，我们一样根据2016的那一篇 paper， 我们去从这个复杂的 cell cluster 中，找出一条最具代表性的 single closed left span。那这条路径呢，是根据雷雨包本身特征变化最小的路径。那当我们把这个路径给找出来之后呢，我们再重新根据我们从二维雷达上的雨包资讯，再配合我们的三维的雷达资料，在我们三维雷达资料中重新建构出我们三维的雨包资讯。那建立完之后，我们就可以去更新我们的雨包的特征。那这个卡伦中这些蓝色的落就是我们利用三维雷达更新的一些雨包的三维的特征资讯。那在我们把资讯都更新完之后呢，我们可以把每个雨包的特征，把它随着时间把它画出来，就是像图中实线的部分。那可以发现这个部分，这些实线表现得非常的不平滑。那这是因为我们所使用的模型本身的误差所导致的。那为了降低这些误差，来让我们的 model 去有更好的训练资料，我们会用一个4次方程式去 fit 它，来降低我们的 error 的误差。那接下来是我们的 model。那我们使用的 model 是 LSTM encoder decoder model。那我们的资料呢，是使用由英国气象局所提供的 3D 的雷达气象资料。那我们会先有4个 input 的 sequence， 然后让它预测后面3个 time step 的资讯。那我们根据前面的一些方法，我们从三维雷达中可以萃取出将近6000笔的雨包的特征资料集。那我们根据8:2的比例，切出4700多笔的训练资料，以及接近1200笔的验证资料。那同时，我们为了去调查说，就是是否三维的资讯可以帮助我们的 model 去预测我们雨包的特征演化，我们设计了3种不同的 model input。那第一个呢，是我们只使用2维的雨包特征作为我们的 model input。那第二个呢，我们是结合了从3维得到的雨包核心的高度资讯，与原本的2维的雨包特征作为我们的 model input。那第三个呢，就是我们只使用我们从3维得到的雨包的核心高度资讯做我们的 model input。那接下来这边是我们 model 的训练结果。那图中可以发现，我们 model 呢并没有产生 overfitting 的情形。那我们从上面这3个特征，就是椭圆形的短轴、长轴还有面积来看，我们可以看到，就是蓝色这条线，就是我们只有使用原本2维资讯作为 model input 的表现是最好的。然而，当我们在预测雨包的强度资讯时，跟刚刚的特征不同的是，反而是我们只有使用我们得到的雨包核心的高度资讯作为 model input 的表现是最好的。那接下来呢，我们把我们的结果把它画出来。那这边呢，灰色实线的部分是我们的 ground truth， 然后黑色虚线的部分是原本的 nowcasting 的 model。那因为原本 nowcasting model 并没有办法考虑雨包的特征演化，所以它是一条水平线。那可以看到的是，我们的 LSTM model 不管是在有没有使用3维的资讯做我们的 model input， 它的表现都比原本的 nowcasting model 还要好上许多。那再来呢，我们使用我们的 NAE 的方法来验证我们的 model 表现。那首先上面3个呢，就是我们雨包的几何特征，就是我们的面积、长轴、短轴等资讯。那从这个图中发现，我们雨包我们的3维的资料并没有提供 model 太多的帮助。然而，当我们在预测 语包的强度资讯时，我们可以很明显的发现，有使用三维的资讯作为 model input 的表现比没有使用三维资讯作为 model input 的表现还要来得好。那另外呢，我们这边也是有刻意的去延长它的预测 lead time。我们原本只有让它预测到15分钟这边而已，那我们这边把它刻意延长了1倍。那可以发现到，随着后面时间的增加，我们的 error 也是呈现指数型的成长，但绝大部分的表现还是比原本的 nowcasting model 还要来得好。那再来是我们 uncertainty 的部分。那我们这边设计了2个 uncertainty 的方法来做我们 model uncertainty 的计算。那只是因为时间的关系，我们这边就只展示一下结果。那我们的结果表明，我们的 uncertainty 可以很好的包覆住我们的 ground truth。那接下来是我们结论部分。第一个就是本研究提出了一个 LSTM model， 可以很好的预测我们语包的特征演化。那第二个就是在三维的雷达资讯在我们预测语包的强度时，可以提供一些我们 model 额外的帮助。然而，当我们在预测语包的几何资讯时，三维雷达并没有办法提供太多的帮助。那最后就是我们有提出一些 uncertainty 的计算方法，但只是这边因为时间关系，就是没有办法去讲这样。对，好，以上是我的报告。
非常好，刚好 just in time。OK， 好，谢谢宇生哈。那我们邀请audience 还有我们老师们来提问。Any question from the audience？
嗨，我是那个阳明医学系的学生啊，我是实习生，然后我有几个问题想问，可以问吗？
当然，欢迎。
OK 我想第一个问题是，现在时间序列的模型有很多，像 LSTM 你提的，还有 GRU Transformer， 或是甚至把它摊平做 MLP 也可以。那我想问的是，为什么是 LSTM？
会用 LSTM 是因为我们之前在做 literature review 的时候，发现大部分 paper 都是先使用 LSTM 作为我们那个就是做 rainfall nowcasting 的预测模型，所以我们就是先跟着 paper 去做这样。对，
所以没有就是类似 ablation study 之类的尝试吗？
我目前是没有。
OK， 那我还有第二个问题是想问，就是要处理2D 资料很多种方法，像 diffusion 是用 UNet， 或者是它用 attention 的机制来拟合，然后或是像 StyleGAN 或是类似的 ResNet 是用 convolution， 然后Vision Transformer 也是利用attention 加 feedforward。那我想请问的是，在处理2D 资料的时候，你们是直接把它摊平吗？还是有做什么前处理？
这边的2D 资料，像你刚才说那个，就是其实现在 nowcasting 也是有分成2个，第一个叫做 field base， 那它就是会直接做整张的雷达影像，就是去做那个预测。那这可能会比较像你刚才说，就是用 diffusion model 那些来做预测这样。那我们这边用的是用 RGB base， 那它跟那个刚才 field base 最大的不同的是，我们会把它从2维的影像中把它辨识出语包出来，把它变成一个一个的值，就是像这个样子出来。对，所以我们2维的资讯是靠一些已经开发好的演算法就是去做的，就是并没有用像是2维的方法去做我们2维的资料处理。
那我想请问，如果只提取其中的某一部分资讯，会不会造成资讯损失？就是
会造成资讯损失。
那为什么会就是那既然有 aware 这个问题，那我想请问是有做什么方法来解决吗？
像我们那时候的目前的方法比较像是损失的部分，可能就是会用这种 fitting 的 model 的 fitting， 就是去有点像是做内插的方式，就是去找出它中间缺失的部分这样。
好，谢谢。那我耽误你的时间，谢谢。那我问题就要这个。
谢谢你的提问。好，那 Any question from the audience？ 有没有什么问题，或老师们有没有提问？
那宇生，我很快的请教几个问题。那个，我觉得你报告很清楚。对，这个你有一张图，上面有 XYT 嘛，对不对？是这个二维 XYT， 然后呢，你后面又说就是这个可以 identify 雷雨包的这个 centroid， 然后是 XYZ， 所以这边我就不太懂，就是你是怎么从 XYT 然后得到这个雷雨包的高度的？就雷雨包高度这件
高度部分就是我们这边就是有后续就是有重新的，因为我们最开始用的是只使用2维的雷达，那我们就是再从2维雷达中就是照它的就是 XY 的坐标，重新的去到我们的3维雷达去找它的资讯。
就是你有2维的跟3维的分别做这样子。
对。
那你现在的这个模型里面，你有考虑到地形的效应？
没有，我们就是完全就考虑，比较像是大气中的就是雷达资讯这样。对。
那你那个最后面你说到你有做到 uncertainty 嘛，对不对？这个部分我也觉得很好。那个你可以简单说明一下，就是你 uncertainty 大概是几 % 吗
？uncertainty 的话，看一下。
大概你对于你的 prediction， 你有这个，比如说
就是我去计算一下我们 uncertainty 的 hit rate 这样，然后就是那我这边只有计算到3个 time step， 那目前都是第一个的话，它的 hit rate 大概都是80几90这样。
好，谢谢。
谢谢。那其他老师有没有要提问的？好，那我问几个问题哈，宇轩，那个你到那个你的 prediction 哈，你那个 loss 那些 prediction 哈，先厘清一下，你现在的预测是这些都是一个 regression 的问题，然后全部都把它预测出来吗？就是一个 model 预测所有的值吗？还是？
没有，一个 model 预测一个值这样。对。
OK， 所以你等于是好几个 regression 的 model。
对。
那你有尝试一个 model 就把所有的都预测出来吗？
没有，因为那时候我想要去就是测试说就是3维雷达资讯是否对我们预测有帮助，所以就是我每个值都是分别就是去做这样子的测试，这样。对。
但只是 network topology 都一样吧？
对，都一样。
OK， 只是 weight 不一样了哈。OK， 那我有注意到，就是这里哈，这个 area 好像表现的特别不好，是不是？我如果没有看错的话，还是说 area 本来就比较大？因为你这个是绝对值。
对，就是这边应该是我的，应该是 area 本身值就比较大，这样。像我们这个它的上面这样给它单位是 km， 然后可是 area 它的单位就是 km 平方这样。对，所以它的本身值就是会比较大这样。
OK， 但是看起来它才是比较 decay 的比较慢的哈，就是其他都蛮快就下去了。应该是吧？那它有什么特别？为什么它特别它的那个 decay rate 跟人家不大一样？你的 hyper parameter 应该都差不多嘛哈？
这个原因我觉得有可能是要回到这边，就是我们在 model 去做range 特征的辨识的时候，它会有一些误差。那时候我观测到说，就是 area 的误差会是里面最大的，因为它本身值就比较大，这样。所以就是即便我做 polyfit 完之后，它的影响还是最多的。对。
OK， 好，那这个有 reflect 到最后的 uncertainty 吗？就 error 跟 uncertainty 还是？
有，就是最后面的 uncertainty 其实我们是舍弃掉 area 的。看一下，再盖那个，对，就是我们这边 uncertainty 我们只有，就是我们没有去做 area 的计算这样。对。
I see。OK， 好，很好。OK， any question from the audience？ 老师们有没有问题？
我想再问一个，宇生可以回到16面，可以解释一下为什么用4次方吗？还是常用的？
没有，就是我们自己去 有点类似 try and error 的方式，对，然后我们发现可能就是4次方以上它的 fit 是比较好的，但只是我们怕太高次方可能会有点类似 over fit 的样子，对，所以我们就是只用4次方这样。
哦，就是尝试过1、2、3，然后发现
对
4就好。哦，那5还会更好，只是怕 overfitting。
对，就是越高基本上是越贴近我们这个，但只是怕会 overfit 这样。
OK，好，谢谢。
那我 follow 这个问题啦，哈，你为什么不就直接用 ML train 一下简单的 polynomial， 然后去看看到底哪一个表现最好就好了？为什么要指定4次？
感觉是可以尝试，
好像不需要去指定它了哈，就是反正就 data tell the story 嘛，啊，他自己去。OK， 好。OK， 好，那老师们或 audience 还没问题 ？Any question? Final call. Okay. If not, let's move on. Okay, let's move to the our fourth presentation by Rita.
我问太多了吧
Aritra, sorry, Aritra. Yeah, Yushin, you can mute now.
Yeah, can you hear me?
Yeah. You want to speak couple sentences so I can hear the well.
Yeah, so can you hear me?
Yeah, it's good.
Yeah, so
Okay, when you're ready, let me know. I'll start counting the time. Rita,
yes, I'm
when
ready.
you're ready, let me know.
Yeah, I'm ready, Professor.
Okay,
Start.
good. Start counting the time.
Good evening, everyone. I'm Aritra Pal. I'm the PhD candidate in the Department of Civil Engineering at National Taiwan University. Today, I'm going to present my research on automated activity level progress monitoring from visual data and schedule through digital twin construction. And my advisor is Professor Patrick Shea and Professor Jacob Lee. So here are some of the awards and what I have received during my PhD. So let's start with the introduction. So till date, many construction projects rely on conventional progress monitoring using paper-based method. So one of the major problem of this method is quite time consuming because it is manual, and we cannot get the 3D information directly from this data. So at the same time, we have seen that increasing availability of visual data and text data can create a unique opportunity for improving the construction planning, as-built modeling and progress monitoring methods. So with the availability of this data, we can actually integrate them in one platform, and then we can use different machine learning and deep learning algorithms to get more insight from the data. And then we can use this digital twin construction system to understand this data visually and then take corrective and preventive actions. So in the previous study, people have mostly focused on vision-based progress monitoring by two methods. One method is called occupancy-based method, where people have compared BIM model with point cloud and then try to get the progress data. But one of the major limitations of this kind of method is it's only depend on the geometry modeling. So getting the progress status is difficult. To overcome this situation, people have proposed appearance-based method. So in appearance-based method, researchers have actually taken image patches and then trying to classify them for different construction materials and try to present progress from that. But this type of method is only applicable if the building element is started or not started, completed or not completed in that situation. But it cannot report the progress in terms of percentage. So the problem statement, what I'm going to address in this study is, the first thing is the activity level progress monitoring is still challenging using the existing method. Secondly, the existing methods only report progress in binary form, that is built, not built, or completed, not completed. And in the third case, the existing methods rely on 4D BIM for comparing the progress with the plan. But in this case, we have observed that 4D BIM creation is a troublesome method because we need to manually match the building elements with construction activities. So to overcome these challenges, my research objective lies in this way. So my main objective is to create and validate a methodology for activity level construction progress monitoring, especially from visual data and construction schedules through digital twin construction. So this research objective can be divided into two tasks. The first task is to develop an activity level progress monitoring system that utilizes as planned beam and on-site images to report activity % completion. And on the second step, I would like to link this activity % completion with the project schedule by automatically linking the reality model and the project schedule. So the first part of my research is progress estimation and visualization. This is actually divided into 5 steps. The first step is 3D reconstruction, camera pose estimation, and beam point cloud registration. The second step is detection of elements that are under construction. The third step is orthographic view synthesis. The fourth step is progress detection and percentage completion estimation. And the final step is project progress visualization. So in the first step, when we get a 4D beam and we create a point cloud using SFM method from site images, we can register them in the same coordinate system so that the beam and point cloud lie in the same 3D space, and we can get different insight for progress monitoring. So after registering the beam and point cloud in the same coordinate system, we can actually check the bounding box of each beam element and then try to count the number of points enclosed in those bounding box. And if that number exceeds a certain threshold, so then you can see that this element is under construction. And this kind of check is required because when going forward, we can eliminate those elements, those are not yet started, and we can focus more detailed progress monitoring for those elements which are under construction. So for more detailed progress monitoring, we have proposed an evidence-based method where we look into the surfaces of each building element and then try to detect the progress from that. So in this case, actually, we have proposed 2 methods. In one method, we have proposed where the element is completely visible from one camera view. So there we can actually back project the element on the camera plane and also back project the element in an orthographic camera plane. And then we can use homography metrics to transform them in the same coordinate system. And in the other case, where the element is not completely visible, we can create new views, orthographic views, by using NARF. So NARF actually take this information like location and viewing direction and then emit color and volume density. And by reducing the rendering loss, we can create more orthographic views. And here are some of the results from the NARF model. So here you can see a long element can be seen in 16 different views, and those are correctly got from the orthographic view. And when you compare the NARF result with the original result, you can see that the NARF result can get around 91% similarity. So once we get the orthographic view of the element surfaces, we can train a deep learning model for image segmentation, and then we pass those orthographic view to detect the progress from that. So here we have mainly focused on 6 different construction activities, that is concreting, formwork, reinforcement steel, floor tile, and wall tile. And we can see that our model can predict those activities pretty well. And for this purpose, we created a data set with 2000 images, and we trained the model with 70, 20, and 10 split. So once we finish the progress detection, from the mask area, we calculate the percentage completion for each progress element. And then we link that progress information with the project schedule. So here are some of the results. You can see that our method can accurately detect the progress percentage with 5.63% error. And this method can be applicable for both indoor construction scenario and outdoor construction scenario, and for different linking purposes where one-to-one linking is there or where many-to-one linkages are also available. So next, we can visualize the progress status on 3D beam model and also point cloud model. So the next part of the research, as I have already mentioned, that we'll be looking into how we can update the project schedule with progress information. So for this part, we need to first detect location, object, and task information from the reality model. And also we need to detect the same information from schedule activities and then match them together. So the first part is pretty much same as what we did in the previous study, but we'll mainly focus on the second and third part in this part. So for one case where we do not have a BIM model, we can also detect different building elements by using semantic segmentation model. So here we have used a Stanford dataset to train our segmentation model, and then we can detect different building elements like ceiling, floor, wall, column, beam from that point cloud. So here are some of the results, and we can see that our method can correctly predict these building elements and provide good insight for progress monitoring. And so next, the same information, that is location and object information, we can also get it from the project schedule. So for this purpose, we have used GPT-3 model to solve named entity recognition problem. And we can see that if we given a construction activity, it can clearly detect task, building element, material, location, all this information. So in the next part, we try to match these information, the information what we have collected from the 3D model and the information what we have collected from the construction schedule, and then match them in the same position so that we can know that which activity is linked to what kind of progress. So for this purpose, we have actually converted this information into word embeddings and then sentence embeddings, and then finally used cosine similarity to check the similarity between this information. And once we achieve a certain amount of similarity, we can say that the matching is correctly done. So using this method, we could achieve around 95% of the accuracy. So here is the conclusion of my study. So in this study, we have proposed activity level progress monitoring method, and that could actually detect progress percentages with less than 6% error. Then we have proposed NARS-based novel view synthesis method for orthographic view synthesis that can actually achieve around 91% similarity with the original images. And then we have proposed the automatic alignment of project schedule with reality model. And that performance is also quite satisfactory. And that can be useful for progress update in the later case. And also the use of large language models such as GPT-3 with very few short learning, we could achieve around 98% accuracy. What we couldn't do with other kind of transformer-based natural language models. So in the future, we have planned to extend this research for different construction activities, because as of now, the research is quite limited only to the structural element detection and structural element progress monitoring. And these are my publications from this research topic. So I have almost six journal papers and 6 conference papers. And this is all about my presentation. Thank you for your listening.
Thank you, Arita. Very nice work. Okay, so now we invite a question from the audience.
Hi, Arita.
Oh, yeah.
Yes, Professor.
Can you hear me?
Yeah, Professor, I can hear you.
Yeah, very interesting. Excellent. So I just have one general comment. So suppose there is a discrepancy between your BME model and your construction site.
Yes.
How you plan to resolve this issue? Because you need to register your point cloud onto your BME model, right?
Yes.
Have you encountered such issues? And then if yes, how you resolve it?
Yeah, Professor, your question is quite right. Because in my first research, I have completely relied on the BIM model, and then we have actually compared the BIM with the point cloud model. But in my second part of my research, I have also encountered similar problem as you have mentioned, that where BIM model is not updated, so that we cannot directly link it with the project BIM model. So what we decided in this case, instead of relying on the BIM model, we can actually detect the BIM building elements by doing the semantic segmentation instead of relying on the BIM model. And we can actually register this point cloud model with a ground control point to get the information related to the location, and we can use semantic segmentation model to get the elements, basically column beam, and then we can use like float to float inference to check that whether we can get the progress status from that. So this is how we have resolved that issue.
So essentially, you are saying that you don't need BME model. You just need the original length of the column, right? Say, for instance.
Yeah, you can, because see, if we have a BIM model, the process is much simpler because we don't have to use learning-based model. We can just get the bounding box from the BIM model and then segment the point cloud to detect the elements. But if you do not have a BIM model, then you need learning-based model to detect building elements. And then you need to use different algorithms to get the segmentation of each elements and then link it to the project schedule. So yeah, this is also another objective of our second part of the research. Like in a lot of cases, we have seen that PIM models are not updated properly every time. So how can we use still we can do progress monitoring if we do not have an updated PIM model?
Yeah, great. Thank you.
Thank you.
Very good. Other question from the audience? 老师们还有没有什么问题？ yeah, go ahead.
Yeah, it's really nice work. I saw the earlier part. I think when you're kind of detecting the structural element, it seems the different material has an impact.
Yes.
And then in the final conclusion, you also mentioned about you want to extend your work to not just the structural element.
Yes.
So can you briefly just what do you expect? What kind of what will be the main challenge when you want to is material or something else when you want to expand it from structure to other element?
So Professor, the main challenge is as of now, because the segmentation model what we have is mostly on the structural elements. But if we have activities like clustering, so it's not represented by a structural element. So then we have to rely on material appearance. So in that case, also we need to extend our research for different material appearances. So yeah, these are the two limitations as of now we have. Like if we completely rely on structural elements, so we can detect it from point cloud segmentation. But in case if we have like different layer of materials coming on top of each, like you can see like plastering and then painting. So it is not detectable by point cloud segmentation because point cloud only gives us the surface. So I think in both ways we can extend our research for future on-site applications, I can say. Yes.
Thank you.
Thank you.
Okay, good. Any other questions from the audience? 老师们还有没有问题？ Richard,
yes.
In your first part, using this so-called bounding box to
Yes.
check whether this element is present.
Yes.
Okay, and when we do this point cloud through LiDAR or through structure from motion, it's always a resolution problem. Okay,
Yes.
so every time you do the point cloud, you could get a different point cloud.
Yes.
So how do you determine? For example, if you do different kind of point cloud, you might have different kind of points, and the resolution will be different. How do you justify this situation for all kinds of point cloud scanning?
Yes, Professor, for this part, I think quickly skip that part. So basically, for this method, we also kept the threshold value. So to increase the bounding box, because as you have mentioned, like if we make a point cloud from structure from motion, we have a lot of noises, and if we are using laser, it's far better point clouds we can get. So we can have a experimental threshold to adjust the bounding box dimension so that we can achieve at least. And this is also a rough check. I'll not say this is a very good check for checking the elements, but at least it will give us that this many number of elements are under construction, so that our algorithm can only look into those elements instead of checking the entire model. Because when we want to check the entire model, all the elements, then it is quite time consuming and also quite expensive. So by doing this method, actually we are trying to reduce the number of elements, and also this threshold is experimentally set. So basically, if we have a point cloud from structure from motion, we set this threshold a little bit higher so that we can have better understanding. And if we have a point cloud from laser, I think we can reduce this threshold to get the numbers.
Okay, sure. Very good. The second question is about your point transformer. The very end. Go to the very end.
Yes.
Yeah, right here. Go up. Yeah, right here.
Yes.
Okay. So if you look at the result, this is from point transformer, right? It just
no, Professor, we have used soft group model.
Oh, soft group. Okay.
Yes. Yes.
But anyway, it's your input is point cloud, right?
Yes, yes, Professor.
And then your segmentation result is also pixel-wise segmentation, right?
Yes, point-wise. Point-wise.
And this result is unbelievably good.
Yeah.
It's pretty good indeed.
Yes, Professor.
Can you-
Actually, this data set, and as I already mentioned, that if we have only this items like floor, column, beam, and the S3 Stanford data set is also quite a huge data set. And also we have supported with some of our own data set. So we have increased the data set. So it can detect well. But yeah, of course, if the structure of the element is weird, like not a rectangular shape, it's a circular and all this kind, then we may encounter difficulties in detecting the elements.
I see. So you have a pre-trained model from Stanford database.
Yes.
And then you start from their weight. I
Yes.
see. Okay,
And then we
okay.
just use our data to find in that model.
Okay. Do you have a class that they do not have? I mean, I'm not sure. You have a
No,
setting, you have
we
compound.
only have all the classes what they have. Like these are the classes they have.
Oh,
They
okay.
have 13 classes. So you only choose 6 classes from them. So for our case, so there is no
But
new
for
classes
your
here.
But for your later application, you might have a class that do not belong to here, right?
Yes. Yes.
And do you have you thought about this?
Yes, Professor. In that case, I think as we are mostly focusing on supervised learning, so we may need to create more data for that class and then include it in the existing data set so that you can train our model again. But yeah, definitely we can think about a different unsupervised learning like clustering-based methods for doing initial segmentation and then fine-tuning it with doing like deep learning model later. So
Okay,
yeah, but
good. All right. Any question from the audience? Well, if not, Richard, please release the screen sharing. Okay, we're going to do the gradient, and this will be very difficult, I know, but we had to do that. So all the professor will send their result to our secretary, and then we will announce the winners today, which is quite harsh, all right? And I'll stop recording from now. Indeed.
So can you hear me, by the way?
Yeah, that's very good. Yeah, I start recording now.
So if you, I mean, at the end, didn't manage to get the first place or first runner up, don't take it personal. Okay, it's very hard for us. Okay, you guys are very good.
Okay, I guess we now have a result. Okay, we now announce the winners today. Okay, we have 2 winners, as I mentioned, and these 2 winners are Aritra and Jimmy. Let's congratulations them, Aritra and Jimmy. Okay, and Aritra, you're the first place, so you've follow-up application to go for the President Award. Okay, I hope you can finally seize the President Award for our group. Yeah, you carry our big expectation. Congratulations.
Thank you, Professor.
Congratulations, Jimmy. Congratulations, Aritra.
Thank
Yeah,
you.
thank
I guess there will be another PK in the department level, right?
Right.
Okay.
Plan to. I'm not sure how to
Okay.
do that, but all the 学术委员had to do that. I'm not
Okay.
sure how we're going to do that, but it will be hard. Yeah. Then we will have this kind of PK result for the university, and I'm not sure university will PK again, but
No, I don't think so. Yeah, I don't think so.
okay. But anyway, Aritra and Jimmy, and congratulations on your good work. You both win the team award. for this year.
Thank you.
Yeah, very nice job. Yeah. 几位老师有没有什么 comment 要给他们？
Congratulations.
Thank you.
Thank you. Thank you.
Congratulations, it's really good work. I think all presenters give really good presentation today. And also they all produce really impactful research. I think that's the most critical part. And then you all try to also demonstrate the impact of your work. I think that's a very good point to highlight that. Thank you, good work.
Lisa?
So just want, even after your graduation, remember to continue to create your impact. That's very important.
And Patrick? Yes,
I think they are just the representatives from different groups. And then I would like to congratulate all the students who are graduating this academic year. And for those who are still working hard for graduation, keep working hard. Okay.
Thank you.
Okay, very good. Yeah, with that, I'd like to close today's session and thank you all for attending this. And I hope everybody learned something from this very well-structured, well-prepared presentation. Congratulations. And with that, let's say farewell. See you guys. Bye-bye.
Yep. Good night.
Bye-bye.
Bye-bye.